There we go. I will. All right. I will begin with a word of prayer. Sorry, I have used precious class time to talk about, passing the class. I guess that matters, though, right? Yes. To you, yes. I mean, I want you all to pass. Don't get me wrong. It does not give me joy. Despite appearances, it does not give me joy to fail students. It's actually not the case. I mean, on occasion, there's a student that I really want to fail, and I'm like, haha. But it's fairly unusual. There's really only a very small subset of the students who provoke that response in me.
Is anybody else classes?
No, nobody here. No, you're nowhere near that. No. No, you guys are fine. The thing that will provoke that from me is people who are arrogant and at the same time refuse to work and or to acknowledge that they don't know what they're doing. This is not an opportunity to name names. And that is not him. But anyway, he's adorable. Anyway, I will begin with a word of prayer, finally. Heavenly Father, we thank you for this day. I thank you for these students, in fact, all of them. Help us to have a good day today and to learn a little bit more about generalized eigenvectors. Amen. All right, so let me get to it. Let me begin with a definite thing that will not help you on the next test, or really in life in general. Let me begin with a little theorem. If v1 and v2 are eigenvectors with eigenvalues lambda 1 not equal to lambda 2 respective, for A, then v1, v2 is linearly independent set. Now, in the video I've asked you guys to watch, I prove not just this, I prove a much more greedy version of this with multiple eigenvalues. But I think it's good, it should be edifying if I just go through this. This is a typical test question going forward. So if I want to prove that v1, v2 is a linearly independent set, I should do what? So, yeah, so let's, right. So let's suppose that AV1 equals to lambda 1 v1 and AV2 equals to lambda 2 v2, where v1 and v2 are what? Not equal to 0, and my eigenvalues, lambda 1 and lambda 2, are distinct, all right? That's the data that I'm working with. I should assume that at the start of the proof, because this is a direct implication proof. We start by assuming what the data is that we're given. And now I'm going to test for linear independence. So consider, that feels better. C1v1 plus C2v2 equals to 0. Right? I want to give some series of arguments that proves that C1 and C2 are 0, or perhaps we'll go by some contradiction. I'm not sure. All right, so what I suggest, so would you guys want the, let's see here. I really like the direct proof, which is a little bit sneaky. But let me just be less sneaky and just, what happens if we multiply by A? We get C1A1V1 plus C2AV2, right? So this is C1 lambda 1 V1 plus C2 lambda 2 V2, and that's all equal to 0, right? Let's give that thing a name. Let's call this star. All right, so the proof that typically is given to students at your level, it's not very clever. It's based on this argument and then a proof by contradiction. So if I wanted to contradict the linear independence of this set V1, V2, what would that mean? Right. In other words, I could assume that V2 is equal to like k times V1, right? For some constant k. The reason I can assume k is not equal to 0 here is because I'm already assuming what V1 and V2 are what? They're eigenvectors, right? Which means that they're non-zero. So if there is a linear dependence, I should be able to define a non-zero k such that one is a multiple of the other, all right? Then what do? Plug V2 equals to k V1 into star. What's that give us? We've got C1 lambda 1 V1 plus C2 lambda 2, what we got here? K V1 equal to 0. Does this help us? Well, does it say that though? I mean, I think what we have at the moment then is C1 lambda 1 plus C2 k lambda 2. That times V1 equals to 0, right? We're assuming that V1 is non-zero, so what does that tell us? Right, so yeah, we got C1 lambda 1 plus C2 k lambda 2 is equal to 0. Yep.
I missed it. Why you said V1 is not 0?
Because we're assuming at the start that V1 and V2 are both non-zero. So at this point, I'm like, I mean, it's not, I wanted to find that C1 and C2 are 0, right? It's not quite working out for me. So how should I regroup and like try to rescue this proof? How do you do it? Like this is not going well. I mean, I've kind of gotten to a point where I'm stuck. How should I regroup and try again? This is something you need to do, right? If you try a proof and you're halfway through and it doesn't work, you got to think about how can you repair the proof. I mean, this is something that's hurting you on the test. Is you don't have like a game plan. Like if something goes badly, you got to kind of regroup and try something else, right? So what should we do here? See, what I've discovered here is this is really, if you look at it, take a step back and look at it, this is really the key idea. So I would say we should just go back to the start, suppose everything that we did, begin by the contradiction. All right, so I'm just going to go right back up to here and I'll fix it right there. I would say start by saying, suppose there exists k not equal to 0 such that V2 is equal to k V1, right? What can I do to that? I multiply both sides. I multiply by a, right? Multiply by a. what does that give me? AV2 is KAV1, right? Which is to say that lambda 1, lambda 2 rather, lambda 2 times V2 is equal to K lambda 1 times V1, right? So the same steps I was making in the previous attempt, all right? Then what? What can we, I want to make V's on the same on both sides so I can use that cancellation principle I used down here. Like this was a nice step. It led us to something that wasn't quite as clean as we need. I mean, we need to find something that's clearly a contradiction, and that didn't quite do it for us. How about this? I can convert that V2 into a V1. How can I do that? How about this? Lambda 2, K V1 equals to K lambda 1 V1, right? Because V2 is K V1. That's our assumption here. We're trying to find a contradiction. We're almost there. All right. On a test, if something like that happens, should you erase all that? Probably not, right? If those are good steps, you should probably leave them and say, I'm starting over. This didn't work out well. Please see the back. This is why I make one-sided tests. You have this freedom, yeah? Just saying. This, if I look at this, I can rewrite this as K times lambda 2 minus lambda 1 times V1 equal to 0, right? Thus, K times lambda 2 minus lambda 1 is equal to 0 as V1 is not equal to 0, right? And one of the basic properties of the vector space was that if we have a scalar times a vector equal to 0, either the scalar is 0 or the vector is 0. Great. Now, K was non-zero by assumption, right? So what does this say? Oh, very good. That's one way you could look at it. So you saw the contradiction as lambda 1 and lambda 2 are different numbers, so those have to be non-zero. That forces K to be 0. That's a contradiction. Great. I'm on board with that. Very good. I saw it a different way. I saw it K is non-zero, so I can cancel. And that gives me that lambda 2 minus lambda 1 is equal to 0, which of course also gives me a contradiction, namely that lambda 2 equals lambda 1. But however which of course is a contradiction because we assumed that lambda 1 and lambda 2 are distinct, right? Whichever way you look at it, you have a contradiction here, which means that our original assumption that they were linearly dependent was flawed. So by proof by contradiction, we find that the vectors are linearly independent. Now, if you're like me, this proof does not give you joy because, well, I just don't like contradiction proofs if I can avoid them. All right? So that's the contradiction proof. Here's the direct proof. So just ignore what's in the blue. Here's the direct proof. Suppose C1V1 plus C1V1 plus C2V2 is equal to 0 with the given data. And then the direct proof requires a certain sneakiness. Instead of multiplying by A, multiply by A minus lambda 1 times the identity matrix. All right? So I have C1 A minus lambda 1 times the identity matrix, V1 plus C2 A minus lambda 1 times the identity matrix times V2 equal to 0. And see, by construction, this is the matrix. A minus lambda I is the matrix which annihilates V1. By construction, V1 is in the kernel of this matrix. Excuse me, the null space. And so this is C1 lambda 1 V1 minus lambda 1 V1, which of course is 0. And then you have C2 times lambda 2 minus lambda 1 V2 equal to 0. All right? The first term is 0. The second term is a non-zero number times C2 times V2 equal to 0. But because V2 is non-zero, and because lambda 2 minus lambda 1 is non-zero, this implies that C2 is 0. And once you know that C2 is equal to 0, we can go back to the initial assumption, which let me call star. Then by star yields C1 V1 equal to 0, which implies that C1 is equal to 0 as V1 is not equal to 0. So we've shown that the star equation implies both C1 and C2 are 0. Therefore, V1, V2 is linearly independent. Now, which proof do you like? The contradiction one, right? I mean, that's what a lot of students prefer, because the second proof I showed you requires a certain sneakiness. But this is a sneakiness that you should sort of assimilate as you think about what are eigenvectors and what is their connection with being in the null space of A minus lambda I. All right? All right. So I think I've spent entirely too long on that proof, which means I need to project something. I'm sorry, guys. I try not to, but it's just it is what it is today. Now, if you watch the video I sent you links to, I prove not that, but the generalization of what I just did for not just one, but like a bunch of them, like a list of distinct eigenvectors with distinct eigenvalues. And I prove that if you have a set of eigenvectors with distinct eigenvalues, they're linearly independent. Furthermore, I prove that eigenspaces, all right, if you take a bunch of eigenvectors, all with eigenvalue 2, and you take another collection of eigenvectors, all with eigenvalue 3, then the 2 eigenspace and the 3 eigenspace, they're independent subspaces. What does that mean?
They should direct some, well, not necessarily the whole space, but they, right? This was the proof I missed on the test, by the way.
Oh, the proof, yes. Oh, that one, yes. This is not what I'm talking about at the moment. So they're independent in the sense that their intersection is 0. That's all I'm saying at the moment. Their intersection is. Oh, you fixed it already. Thank you. You're experienced. All right. Okay, so major ideas that you need to learn from the video that I've linked in the announcement is that eigenspaces are independent and that there's a connection with diagonalizability, which I'll come back to here in a second. The other big idea we need to talk about is geometric versus algebraic multiplicity, all right? Because this is the key idea that the Jordan form is all about the analysis of, okay? So in particular, what is algebraic versus geometric? So let's talk about a matrix. The determinant of A minus lambda times the identity, this is equal to something called the characteristic polynomial. Or perhaps I should put an x here. Let me put an x. P of x, the characteristic polynomial. It could also be we're working with a linear transformation from v to v, right? So then we'd have t minus x times the identity operator on v, which we just write as the determinant of t minus x for this discussion. All right, so we either look at a matrix or we're looking at a linear transformation, depending on what suits our fancy in the given discussion. I mean, these are two dueling ideas that are essentially the same idea. All right, so we're going to assume for today that p of x has n zeros, possibly repeated, in the field that we're working on, which is either going to be the reals or the complexes. My point is we're assuming that the eigenvalues of our linear transformation or our matrix are in the field of consideration. All right? In this case, that means that P of x looks something like some, well, if you work out the details here, right? If you look at it, if we're working with an n by n matrix or a n-dimensional vector space, the characteristic equation is an nth order polynomial equation. And if you look at the formula, what you're going to see is that the leading term is actually minus 1 to the power n times x to the n. And then a bunch of stuff. Eventually, you get to the constant term. Let's call that C0. I mean, fine, I could put a C1 here plus C0 just to show you my labeling. Anyway, if this actually has n zeros in the field, what that means is I can factor it. I can put some constant, well, I can put minus 1 to the n out front, right? And then I can put like x minus lambda 1 to the m1, and then x minus lambda 2 to the m2, x minus lambda, let's label these 1 through k for the sake of discussion. Oh, let me use little r actually, or big R. R, there. Sorry, that was horrible. M to the r. So this is what the factoring of the characteristic polynomial looks like if all the zeros are in the field, right? We have x minus the root to the multiplicity of the root, whatever that is. All right? This is what it means to say that there are n zeros possibly repeated. How is n related to the m's? N is m1 plus m2 plus mr, right? The sum of the degrees here has to match the totality of the degree. Characteristic polynomial, nth order, where n is the dimension of the vector space that we're looking at the linear transformation on, or A is an n by n matrix, all right? So, given all of this, what is the significance of C0? I mean, there's a couple things we can see from this formula without like a lot of work. Identify. See, if we multiply this out, right? What do we got for the constant term? Well, not quite, right? Because we got minus 1 to the m. We've got minus lambda 1 to the m1, minus lambda 2 to the m2, right? Minus lambda r to the mr. So what do we got? We've got minus 1. That's n. Look, n as in nanu, not m as in mommy, n. So we've got minus 1 to the n, and then there's minus 1 to the m1 plus m2 plus plus mr. Product of the eigenvalues to their respective powers. But what is m1 plus m2 plus plus mr? Well, that's n again, right? So one of the things I'm showing you here at the moment, in probably more detail than I should bother with, but oh well, it's too late. This is n. These are both minus 1. What's minus 1 to the n times minus 1 to the n? It's just 1, right? It's either plus times plus or it's minus times minus. So this is literally just the product of the eigenvalues. Right? That's the product of the eigenvalues. In fact, there's more that you can prove. I haven't quite proved this, but it's in fact true. There's a theorem which says that in fact the determinant of A is equal to this. So one thing to check your work on when you find eigenvalues for a matrix is the determinant of the matrix equal to the product of your eigenvalues, because it should be. If you have a matrix that has determinant 7 and your eigenvalues you think are 2 and 3, well, you're wrong. You made a mistake somewhere. All right. Sorry, I got a little bit off track there. I mean, I'm not terribly off track. So this formula, what do I mean by algebraic versus geometric multiplicity? What is the algebraic multiplicity? Algebraic multiplicity is just whatever these are. And I'm assuming, of course, that the lambda 1, lambda 2, lambda r, these have to be distinct. Otherwise, the m's wouldn't be well defined, right? But so m sub j is algebraic multiplicity. And let's say that p sub j, which will be the dimension of a minus lambda j to the I, excuse me, still messed it up, null space of a minus lambda j to the, times I. This is the geometric multiplicity. So in other words, the geometric multiplicity would be the dimension of the jth eigenspace. So geometric multiplicity is the dimension of the eigenspace. Algebraic multiplicity is the number of times the factor is repeated in the characteristic equation or polynomial. Do you see the distinction? These don't have to match. But what we can prove, and that's what's on the projector right now, is that the geometric multiplicity is at most the algebraic multiplicity. Like algebraic multiplicity is the maximum value the geometric multiplicity can take on. And the proof is right here. So if we have geometric multiplicity p, then we can take eigenbasis v1 through vp and extend it to a basis for the whole space. Then if we look at the matrix for such an operator with respect to that eigenbasis extended, we'll get lambda times the identity in the first p columns. And then we get a pair of matrices over here. All right? I don't care really what happens there. The point is, when you look at the characteristic equation, you get x minus lambda to the p power from this piece, and whatever else happens over here, I don't really care. So that means that x minus lambda to the p is a factor of the characteristic equation. But we also know that x minus lambda to the m is a factor of the characteristic equation, where that m is like maximal. That defines the algebraic multiplicity. Like, that's the biggest x minus lambda factor you can find. That defines that being the algebraic multiplicity. And so it follows that this has to somehow fit that inside it. Otherwise, it would, I mean, this, by the construction of the algebraic multiplicity. So that is to say that p is less than or equal to m, which is what I'm claiming. I've shown you examples, if you watch the videos, I show examples where it may or may not be the case that we actually have as many eigenvectors as we have like repeats in the characteristic equation, all right? Yeah.
Maybe you talked about some here, I haven't seen yet. Is the concept much of spectral circles in here?
No, there are no spectral circles yet. No. Let us say this much. So diagonalizability. What does it mean what does it mean for a linear transformation to be diagonalizable? It means you can find a basis for which the matrix of the transformation is a diagonal matrix, right? That is equivalent to there existing an eigenbasis for the transformation, right? This is also equivalent to saying that the geometric multiplicity is equal to the algebraic multiplicity for every eigenvalue of your transformation. And again, we're working under the blanket assumption that the eigenvalues are all in the field. So like that example I showed you before the test where we had a matrix which had complex eigenvalues, right, for the real matrix, well, that doesn't even fit this discussion. That's a whole other thing, which we'll talk about next class, all right? So do you understand the issue? The question is, what do we do when the eigenspace is not as big as the algebraic multiplicity? Like, what happens when the algebraic multiplicity is 5, but the geometric multiplicity is only 3? What does that mean about the transformation. All right. Well, one of the things it means is that transformation is not diagonalizable. All right. So long story short, what happens in that case is that there still is a standard reference thing that you can convert your transformation to. You can always convert a transformation which has all the eigenvalues in the field into what's called Jordan form. All right. So I want to try to describe that to you right now. So this is section 8.2. I'm going to put this away because I want to write these things out, okay? Well, I'm going to regret this. So I'll just start with what it is. A matrix is in Jordan form if it is the direct sum of Jordan blocks. So let me just start with the most basic one. J1 of lambda is just lambda. J2 of lambda is a 2 by 2 matrix. It is lambda, lambda, 1, 0. J3 is lambda, lambda, lambda. 1's on the superdiagonal. Yeah.
Is J1 the escape of lambda or the matrix containing the escape of lambda?
Yes. I'm not distinguishing between those ideas. J4, lambda, 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 and 1's on the superdiagonal. So like generically speaking, JK lambda would be like lambda times the k by k identity. All right, lambda times the k by k identity plus what I would call it n sub k. Where what is n sub k? Can you see the pattern? It's like it's E1, 2, right? Big E1, 2. Plus what comes next? E1, 2, and then E2, 3. Plus what's the last thing? K minus 1 to k, right? Like that's the general pattern. And the thing that makes this interesting is that this n sub k is nilpotent order k. See, n to the k, n sub k to the k power is equal to 0, but n sub k to the k minus 1 is actually not equal to 0. Actually, n sub k to the k minus 1 is the matrix which is all zeros, except it's got a 1 in the upper right corner. You can already see this, like this is lambda times 1, 0, 0, 1, right? Plus 0, 1, 0, 0. So I'm saying that this is n sub 2. N sub 2 to the first power is not equal to 1. It's got a 1 in the upper right corner, yet n sub 2 squared is 0. It's a nilpotent matrix order 2. So Jordan form is like a direct sum of these things, okay? So these direct sum, what's that mean? So we could have A is like J1, 3, direct sum J2, 3, direct sum J3, 4. So what would that look like? for. This is an example of a Jordan form. So a Jordan form is like the next best thing to diagonalizable. All right, it's sort of almost diagonalizable. It's almost diagonalized. I mean, we can't hope to diagonalize all matrices. Some of them just can't be diagonalized. All right? So in this situation, if you have a matrix in Jordan form, you can study the standard basis and see that it behaves a very particular way. Let's look at another example before I do that. We could have complex Jordan form, right? It could like A equals to the Jordan form of 3 plus 2i, direct sum, the So the things I'm not writing, they're all 0. All right? All right. Now, if you watch the video that I asked you guys to watch yesterday, and I understand if you haven't yet, it's fine. But at the end of the second video that I mentioned, I actually study a Jordan form. That's really that's where my example's coming from. I'm looking at the sum of something like one 2x2 Jordan block and one. These are by the way Jordan blocks. All right. So just to cut through the static here, this is the theorem that we ultimately find. There exists P invertible such that P inverse AP is equal to J. And I should state for any A in Fn by n for which all the eigenvalues are in F. So in other words, assume that we're under the preconditions of this lecture that all of the eigenvalues are in the field. If that's the case, then there exists an invertible matrix P such that P inverse AP is equal to J, where J is so-called Jordan form, which means it is the direct sum of Jordan blocks. What was the case for a diagonalizable matrix? What was the deal? Very similar, right? If a matrix is diagonalizable, there exists a P, right, such that P inverse AP is a diagonal matrix. How did we make that P? What we did was we used the basis of eigenvectors, string them together, put them into a matrix P, then P inverse AP gives me the diagonal matrix using the eigenbasis. To make this happen, you form P by using V1, V2, Vn, a so-called generalized eigenbasis. All right, where this basis consists both of eigenvectors, like we've already talked a little bit about, but also generalized eigenvectors. All right, now I haven't defined a generalized eigenvector yet, but I will here in just a second. So the generalized eigenbasis is formed by taking eigenvectors and generalized eigenvectors, which are arranged in what are called chains. All right, you string them together, and then you can do a similarity transformation to the Jordan form. this is very useful, all right? Now, the mechanics of how we actually construct the P, that's a pain, all right? It's going to take me 20 minutes in next class to talk about it probably, all right? But the neat thing here is if you had two matrices, right? And they both have all their eigenvalues in the field. And you want to decide whether or not two matrices are similar. How can you decide whether or not two given matrices are, what does it mean for two matrices to be similar? By the way, A and B are similar matrices if what? A similar to B. That would be helpful, but that's not enough. If there exists P in, well, let's say GL and F, so an invertible n by n matrix over the field such that P inverse AP is equal to B. So this is what it means for two matrices to be similar. If you can conjugate them by an invertible n by n matrix and get from one to the other. Well, this Jordan form is very interesting because apparently, supposing that the matrix we're talking about has all of its eigenvalues in the field, then we can conjugate to the Jordan form, right? And you can prove that if we had two matrices which are similar, then they have the same Jordan form up to a reordering of the blocks. Like, let's see, let me work through that. So check this out. So let's suppose that Q inverse AQ equals to B, right? Then if I plug in, let's see here. Trying to think how to do this. Well, that says that A is equal to QB Q inverse, right? But we also know that P inverse AP is P inverse QB Q inverse, right? Times P. But what's this equal to? If I'm assuming that we have a Jordan form for that, that's J, right? And what's this? Well, this is, what is this? This is Q inverse P inverse, right? B Q inverse P, right? So what that shows you, that little calculation, is that A and B have the same Jordan form. Because when we work out the theory here, we'll find out that the Jordan form is in fact unique up to the reordering of the blocks. And I think this calculation actually kind of shows that. But so to decide whether or not two matrices are similar, you could see if they have the same Jordan form. How do you find the Jordan form, right? Well, that's actually not a calculation I hold you guys completely responsible for. Your primary responsibility here in this course, because this stuff gets to really prove all this, it's really quite involved, all right? The main thing is you need to come to an understanding of what to do with these blocks, all right? I'll show you if I can get this thing working again here. Oh, you be quiet. Ah. What's that?
Better than Electronica. I told that story in Cal 2 the other day, but
Yes, I usually, if I have to explain to people who Nathaniel is, I always explain it in terms of his reaction to me playing Dead Mouse's maths during a math battle.
actually that was before our first test.
Oh, before our first test?
In Cal 2. Well, actually during our first test, which is why I was so mad.
So, like this matrix, for example, I can look at this, I can tell you that E1 is an eigenvector with eigenvalue 8. I can tell you that E4 is an eigenvector with eigenvalue 8. And I can tell you that E2 and E3 are generalized eigenvectors of order 2 and 3 respective because of the calculations that are down here in a larger discussion we'll have to have next time. But my larger point is, if you have Jordan blocks, you can like identify the standard basis as being a quote-unquote Jordan basis, which we'll define next time. I'm sorry, I spent far too long talking about this potential test question at the start of class, but I think it's for the best. I'll shut up. Thanks, guys.
I haven't looked at the test yet. Did you apply a curve to when you first started protocol?
No.
Okay, yeah, that's what I was like.
No, there's...
I took solace in the thought that I was working on that so much that I didn't study as much as I should have, but like...
No.